Hello everyone, welcome back. In this video, we'll be discussing about the last problem of today's weekly contest, maximum element sum of a complete subset of indices. The problem is very interesting and it is actually a very good hard problem to solve because it is neither that hard so that you require advanced algorithms and it is not that easy as well. So it is a balanced hard problem, I would say. So if you haven't given it a try, I would encourage you to pause and try to solve this problem at least once by yourself. So with that, let's get started. The problem states that you are given one indexed array nums of n integers. A set of number is complete if the product of every pair of its element is a perfect square. For subset of indices 1 to n represented as I1, I2 all the way up to ik, we defined element sum as the nums of I1 plus nums of I2 all the way up to nums of ik. You have to return the maximum element sum of a complete subset of indices of set 1 to n, right? So there are two things, complete and element sum. Element sum is simply the sum of all the elements in the given subset. Complete, a subset is called complete if every pair, if you product them up, it will be a perfect square, right? So for all such complete subset, you will find out element sum and you have to return the one which have the maximum element sum. So hope the problem statement makes sense. Let's try to look at an example. Let's say num says 87357249. Now single element is a complete subset in itself. Why? Because you can see in single element there is no two pairs at all, right? So because there is no two pairs, you can't actually form any pair and hence the product is not possible. So single element is a good subset always. So we have element sum of all the single elements as 8, 7, 3, 5, 7, 2, 4 and 9. So among all of these, 9 is the largest one. So till now we have found element sum value as 9 maximum. Now let's talk about the subset which contain more than one element. So there are two such subsets here, 1, 4 and 2, 8. Now in 1, 4 you can see 1 multiplied by 4 is 4, which is a perfect square number. Hence 1, 4 is a valid subset. And similarly 2, 8, there is just one pair 2, 8 and 2 cross 8 is 16, which is again a perfect square, and hence 2, 8 is also a valid subset or a complete subset. Now element sum of 1, 4 will simply be the sum of 8 plus 5, which is 13. And element sum of 2, 8 would be sum of 7 and 9, which is 16. So among previously we had 9, now we have 13 and 16. So among all of these, the maximum is 16. So till now we have found 16. Now you can't find any other subset which is a complete subset, and hence the answer here is 16 because 16 is the maximum element sum that we could have get, right? So hope the problem makes sense. Now how to solve this? Again, if you haven't tried the brute force solution as well yet, I would strongly encourage you to pause and try to think of brute force solution at least by yourself. So let's start with the brute force solution. We have to find all the complete subsets first. For each of these subsets, we will try to find out the element sum and we will just pick the one which gives us the maximum element sum, right? So in this particular case, let's say there is an array of 16 elements, right? What these elements are doesn't matter if we are trying to compute the complete sum. These elements matter when we are trying to compute element sum. For complete subset doesn't matter. Now what are the complete subsets of this particular set of elements 1, 2, 3, 4 all the way up to 16? The answer is, one possible way is to try out every possible subset. So there can be 2 to the power n subset of this particular set, and what you can do, you can try out every possible subset. For each of the subset, you will find out the element sum and return the one with the maximum element. So basically, let's take an example. So in this particular case, these are the subsets which are valid subsets or complete subsets. 1, 2, 3, 4, all the way to 16 single elements. Double elements are 1, 4, 1, 9, 1, 16, 2, 8, 3, 12, and so on. And so there are subsets with 3 elements as well: 1, 4, 9, 1, 4, 16, 1, 9, 16, and so on. So once you figure out all these subsets, you can simply find out the element sum for each of them and just keep a counter for, or keep a value for maximum, and keep checking which one is the maximum element sum. Now what will be the time complexity of this entire solution? First of all, you are trying to find out all the subset. So there are 2 power n subset, right? Now for each of these subset, you have to first understand whether the current subset that you are talking about is a complete subset or not. So in, you can have a subset of 2 comma 3, right? This is a valid subset, but this is not a complete subset because 2 cross 3 is 6, which is not a perfect square, right? So you have to first figure out whether it is a valid subset or not. So in worst case, your subset will contain all the n elements, right? Now how will you verify whether a subset is a complete subset or not? The definition is, for every pair of elements, the product should be a perfect square. So what you can do, you can, for a given subset, let's say you're talking about this subset, you will try to iterate over all the pairs and find their product and see if it is a perfect square or not. So finding a whether a number is a perfect square or not can be done in order 1 time roughly. So ignoring that, we are iterating over all the n square pairs, right? So this is first thing we are doing to figure out whether this subset is a good or not. Now after we figured out whether the subset is good or not, we want to find the element sum. For that, we are again iterating over the subset. So again, the subset size can be n in worst case. So in total, this is the time complexity of our current solution, right? Now surely this will not pass because n is very huge, 10 power 4. Even this n square is also not will not be allowed in the particular solution because n is up to 10 to the power 4, right? So we have to optimize both this and this from our time complexity. Now let's first try to understand how to optimize this n square, because this 2 power n, optimizing this is harder than optimizing this, right? So let's first try to understand if we are allowed to iterate over all the subsets somehow, then how we will able to make sure that whether a subset is good or not in less than order n square time. So this is your new problem. The problem is, you are given a subset, you need to just say yes or no whether the subset is good or not in less than order n square time. In order n square time, we have already seen we can just simply iterate over all the pairs x comma y and see whether x cross y is a perfect square or not, right? Now I would encourage you to pause and try to think at least for 5-10 minutes how you can solve this particular problem. So whenever you see all the pairs x and y, right, and you have to optimize, the first thing you should try look for is, can I, like, given an element, let's say I1, can I figure out what I2, I3, I4 and all these things would be? What are the possible values of I2, I3 and all other things? If you are able to do so, then you don't need to iterate over every pair. With I1 itself, you can simply figure out what I2, I3 and all others could be, and based on that you can actually solve it in better than order n square time, right? So let's take an example. Let's say in this case we want to figure out whether ix cross xy should be a perfect square or not, right? Now let's take I1. Now there are 2 possibilities. I1 is a perfect square itself, or I1 is not a perfect square, right? Now if I1 is a perfect square, it means whenever you multiply I1 with any of this here, that should also be perfect square only if the other element is a perfect square. So in other words, we are saying that if I multiply I1 with some ix, I1 itself is a perfect square. So basically every factor here occurs twice. So if I1 has a factor of 2, I am sure that 2 occurs even number of times. That's what perfect square means, right? And similarly, if 3 occurs in I1, 3 will also occur even number of times, and so on and so forth. So basically this entire thing is cancelled out with each other. Now in ix, if this entire number has to be a perfect square, all the factor of ix should also cancel each other. In other words, ix should also be a perfect square, right? So if I1 is a perfect square, we know that all of these must be a perfect square, otherwise I1 cross that number will not be a perfect square, right? Similarly, let's talk about the other case where I1 is not a perfect square, right? So in that case, what we are saying is I1 has some factors, right? Let's say 2, 3 and 5. I1 has these factors. Among these, one of these or few of these doesn't occur even number of times. In other words, let's say 2 occurs 4 number of times, 3 occurs 3 number of times, and 5 occurs 4 number of times. So we can see this is a perfect square. This is forming a perfect square. But 3 power 3 is not a perfect square because 3 occurs 3 times. So only 2 can be paired up. 1 3 will be remained at the end, right? So if 1 3 remain at the end, whenever we multiply with something, if this entire number has to be perfect square, ix should also has just one extra 3, no more, no less, right? So if ix has one extra 3 and one extra 2 as well, this number will not be perfect square. But if ix has exactly one extra 3, then I1 cross ix would be a perfect square. In other words, what we are saying is, what we need to make I1 a perfect square, that number is what we must need to make all of these as perfect square as well, right? So if this is not clear, let's take a few examples and it will be much more clear. So there are few subsets that I have taken, and let's see if each of them is a perfect square or not. So this is a subset we are trying to answer whether it is a perfect square or not. Now as we discussed, one, let's take one. So one, how many elements are required, or what factor is required to make one a perfect square? The answer is 1, because 1 is already a perfect square, right? Similarly, so if 1 is already a perfect square, then as per our definition, all the others should be a perfect square. In other words, we should not require anything to make them perfect square. They should already be perfect square, right? So this, if everything is equal in this residual array, basically the number required to make the current element a perfect square, if everything is equal here, then we can say the given subset is a perfect square, is a complete subset, otherwise it is not, right? So let's take one more example. Let's say 2 4 9 16. So in this case, we know that we require 2 to make this 2 a perfect square, right? So this 2 is in itself is not a perfect square, so we require 2 to make it a perfect square. And 4 in itself is a perfect square, so we require 1 to make it perfect square. 9 is also a perfect square, so we require 1 to make it perfect square. 16 is also perfect square, so we require 1 to make it perfect square. Now here, not all the elements are equal, so we can simply say that this subset is not a complete subset, right? Logically as well, if you think, we require 2 to make the first element a perfect square. Now if this 2 is multiplied with any of these here, all of them must require 2 to make themselves as perfect square, otherwise the product will not be perfect square, right? So hope you get the idea. Let's just do one more. So 2 8 18 32. In this case, you can see we require 2 to make it a perfect square. We require 2 to make this one as perfect square, because this has an extra 1, so 2 occurs 3 times here, so this also has an extra 2, so this require 2 to make it a perfect square. Similarly for 18, it also requires 2. Why? Because again, if you factorize 18, it will come as 2 into 3 square, so this 3 square is okay. it should be cancelled by each other. We have a residual of 2, so we require 2 to make it a perfect square, and similarly for 32 we also require 2 to make it a perfect square. So because everything is equal here, then it inherently means that if you multiply any two elements here, right, they will be at the end become a perfect square, because what is needed for this should be sufficed by what is needed for this, and vice versa, right? So hope you get the idea. Basically, given an array, if we are able to find out the residual array, the number required to make every element a perfect square, we can simply check whether all the elements are equal or not. If all the elements are equal, it is a good subset, otherwise it is not a good subset, right? Now what will be the time complexity of this? The only thing that is tricky here is to find out what is the residual number. So what is required to make this number a perfect square? So for that you can do simple factorization and see which factor has odd occurrences, and that you can just put it there, right? So as the value of n is 10 to the power 4 only, notice that the subset is on the value on the indexes, not on the actual numbers. So we will go all the way up to 10 to the power 4. We can just pre-compute everything, and this converting from this array to this array would just be order n operation, order 1 for each of these elements, and we can simply check whether the given set that we have made is contain all the equal elements or not, and based on that we can say whether the given subset is a perfect square, is a good subset or not, right? So we have made this from order n square to order n. So that's what we have achieved. Now notice that this was not the motive. The motive was to, we have removed this n square from here and make it order n, so that's fine, but we have to also remove 2 power n. Why? Because n itself is very huge, and clearly iterating over all the subset is not an ideal thing here. So the next problem is, given which we have to somehow figure out good subsets, or only the one which can potentially give us the maximum element sum. So that's what our target is. So let's start with one. Let's say we are trying to figure out a subset which contain 1, right? Now from our definition of good subset previously, if a subset is already a perfect square, then everything else should be a perfect square as well. If a subset contains, if a number contains requires something to become a perfect square, all other numbers should also require that same thing to become a perfect square. So in this case, 1 is already a good or is already a perfect square number, so every other number should also be a perfect square. So 4, 9, 16, these are all the candidates for this particular subset. Now notice that there are 4 candidates, so you can make various subset like 1 4, 1 9, 4 9, and so on and so forth, right? But do you need any of these? The answer is no. You only need the one which has the maximum number of elements, right? Why? Because every number here is positive. Because every number is positive, you want to take as many elements as possible in your subset, so that your sum can get increased, right? So what instead of iterating over all possible subset of the possibilities here, we will simply take all the square numbers that we have, or all the perfect square numbers that we have from 1 to n, and we will get one possible valid subset, or the largest possible subset which contains 1, right? Now we can simply do the element sum here and figure out what is the element sum value, and keep a variable to get the maximum sum, to maintain the maximum element sum we have seen so far, right? So this is what we have for the subset which will contain 1, or which will start with 1, right? Now let's talk about subset which will start with 2. So for those subsets, we know that 2 is not a perfect square. what is required to make 2 a perfect square? 2 itself, right? So every element that will be there in this particular subset should also have a deficit of 2, right? Now you can't repeat 2 because this is this subset, this set should be the indexes, so 2 occurs once, so 2 can't occur twice. So what will be the next element here? I would encourage you to pause and try to think this particular piece by yourself. This is straightforward after with the last part that we have discussed. So the next element would be 8. Why? Because the next perfect square is 4, right, after 1. So with 4 you can multiply 2. Basically you are saying that 8 also has a deficit of 2, so 8 will be the next possible candidate in this particular subset. Now what is the next one? Next one would be 18. How? Again the same fashion. The next perfect square is 3 square, which is 9, and in this you can just make a deficit of 2 by multiplying it by 2. Similarly the next one would be 32. The next one after that would be 50, and so on and so forth, right? So in this particular case we just have 2 and 8 because we don't have elements after 16, so we will simply go all the way up to 4 and maintain this particular subset. Now we'll just simply sum the value of 2 and 8, and this will be one possible candidate for element sum as well, right? In the same fashion we can do it for 3, for the subset which will start with 3. Now for the subset which will start with 3, again the same thing. The next element would be 27, would be 12, because 2 square is the next square possible, so we want a deficit of 3, so we will just multiply this 2 square with 3 to make it 12, and so on and so forth, right? So hope you got the idea. Basically what we are trying to do is we only want the maximum subset, because every element is positive, so we don't really want the subset which contain less element than it can contain. So in this case 1, 4, 9, 16 has various subset possible, but we pick only this one because this is the one which can give us the maximum element sum. Similarly for 2, this is the maximum subset that can give us the maximum element sum, and for 3 again this 3, 12 is the maximum one which can give us the maximum value. So we will keep on doing this for every element here, and we will maintain the maximum element sum and return that as a result. Now what is the time complexity of this entire solution? Now notice that what you are doing, for every element you are iterating over all the square numbers and multiplying that number with the deficit, right? So in other words, let's say 3. So what you are doing, you know that 3 is deficit of 3, so the next element would be 2 square multiplied by 3, which is 12. The next element would be 3 square multiplied by 3, which is 36, right? 27. Similarly the next one, 4 square multiplied by 3, which is 48, right? And so on and so forth. So what we are doing is we are going in the squares fashion, and we will keep on doing this until we hit n. So how many elements can be there in a particular subset? Root n, right? That's the maximum element possible in any given subset. So for every element we are doing root n operations, or root n, for every element we might get root n number of element in the subset, so we will be adding root n numbers from this array, and then maintain and then do a max with the current element sum that we have. So for every element we are doing root n operation. So this is the overall time complexity of this current solution, and this will surely pass because n is 10 to the power 4, so n root n is around 10 to the power 6, which is sufficient to pass the given time constraint. So hope you got the solution. Next, let's look at the pseudocode quickly. The pseudocode is very straightforward. As we have discussed, we will simply iterate for all the element, and for each element we are trying to find out the maximum subset that is possible if we start with that particular element. So we are starting from I, right, and we wanted to find out what is the maximum subset which is possible with I. So maximum subset would be j cross I, right, and we will simply check if the current index is less than n or not. If it is, we will simply add it to the current sum. If it is greater than n, we know that we have to ignore that because we will not go further. So for every element we do 100 operations and figure out what is the maximum sum that we can get. We start from that particular element, and finally we do result equals to max of result comma sum, right? So this entire thing will give us the maximum value possible. Now notice that some of you might be thinking, okay, for 12, let's take 12. So for 12, what will be the next element? 12 has a deficit of 3, right? So some of you might be thinking, okay, 2 square is 4, so 4 cross 3, 12. So which is not possible because same index can't occur twice. So the thing is, for 12, it actually doesn't matter if you start with 12 or not, because 12, if 12 has to come, what with 3 it will give the maximum value, right? So basically with 3, 12 will also occur in the subset which will have 3. So you already have gotten the maximum value which you can get by 12 with 3 already. So you can skip 12 as well, but to just simplify the complete solution, we have taken everything from 1 to n. So this entire thing can be optimized further as well if you just try to spend some time and figure out which element you have already taken care in previous subsets and which of them you haven't. So with that you can optimize it further, but this is good enough to pass the given time constraint. So if you have watched till this point, again I would strongly encourage you to pause and try to code this entire thing by yourself, because this is very straightforward. Next we're looking at the code. The code is straightforward, as just like the pseudo code. We will simply iterate over all the things from 1 to n. We'll keep a result of max of result comma nums of I minus 1. And this you may or may not do, because with 1 it will already come by default. And finally this you are maintaining a sum, and you are adding to the sum as and when you are getting an element which is less than equals to n. And finally you do result equals to max of result comma sum. So hope this entire solution makes sense. If you have any doubts in this particular problem, feel free to post them in the comment section below. I would be able to answer. If you like the video, give it a thumbs up and do subscribe if you haven't already. And I will see you in the next one. Thank you.